Hello all. Today I'm going to discuss with you the permittivity of graphene. Graphene is a monolayer of carbon atoms and offers extremely interesting physics. Its unique properties may very well make it the silicon of 21st century. For practical applications, it is of great importance to model this material containing the main electromagnetic features. Now, here in this website called photonics101.com, they have given the question. The question is, find out in this problem how graphene can be represented as a thin layer with a certain permittivity and how this can be used for next generation electromagnetic devices. So they have given this problem statement. The statement exactly is, find the dispersion relation of transverse magnetic surface plasmon polaritons supported by graphene embedded in some medium with relative permittivity epsilon d. Here they are talking about epsilon d as the permittivity of the medium on which graphene is placed. So they are suggesting the solution also. They have given the diagram. As we can see, this is the graphene having conductivity sigma, and this is placed over a dielectric whose permittivity is epsilon and thickness is small d. So they are giving the solution steps also. So start from Ampere's law, including the displacement current to figure out a relation between epsilon omega and a three-dimensional sigma omega. Here they are giving it as a three-dimensional sigma omega, or the conductivity of graphene equals to two-dimensional conductivity of graphene divided by small d, which is the thickness of dielectric layer. Assuming a certain thickness of graphene small d. So here they are assuming that small d is the thickness of graphene layer. Regard graphene now as a metallic layer with thickness small d and relative permittivity epsilon m omega. Use the dispersion relation of transverse magnetic surface plasmon polaritons to find wave vector in the limit of vanishing thickness small d. The dispersion relation for the wave vector k rho omega of such an SPP supported by the given layer reads as this. So this is the expression for this is the dispersion relation they have given for the wave vector of SPP waves. So this was the problem statement. They are asking for the dispersion relation of the transverse magnetic surface plasmon polaritons. Now they've given a hint also. In the frequency range, in frequency space, Ampere's law reads del cross B equals mu naught J minus I omega mu naught epsilon R omega E omega. We know that the Ampere's law or the Maxwell's equation in uh, of Ampere's law is del cross H equals to J plus del D by del T. So here they are changing the H to B upon mu, since B equals to mu into H. So we are getting here in the left hand side del cross B, and the mu in the denominator is going to numerator in the other side, and the D del D by del T term in the right hand side is converted to minus of I omega, and D is converted to epsilon E in the frequency space. Hence R comma omega is there. Now they are asking, do you know a relation between J and E involving sigma? So as we know that current density J and electric field intensity E are related to sigma by a simple expression J equals to sigma into E. So can you interpret the conductivity term in Ampere's law as a contribution to the permittivity? So this is the hint they have given. Quite fair it is. One can relate it with this above Ampere's law equation, and then the relation between J and E. One can replace this J by the relation J equals to sigma E, and then take E common, so that one can get a relation between sigma and epsilon. We are seeing the solution also, so that it will get explained in a better way. We have to we have to clarify two things to find the desired dispersion relation. First, we have to find a relationship between permittivity and conductivity. Second, we have to calculate the vanishing thickness limit of the SPP dispersion relation using the found relative permittivity of graphene with respect to the thickness from conductivity to permittivity. So in Ampere's law, del cross B equals to mu naught J minus I omega mu naught epsilon E. Now we can use Ohm's law, J equals to sigma into E, to find del cross B equals to this. Here, as we can see, they have replaced J by sigma into E, and now in the next step they have taken E common, and mu naught also they have taken common. In the other step they have taken minus I omega common. So overall they have taken minus of I omega mu naught into E r omega as common, and the remaining term they have expressed it as a epsilon dash r omega. Now they are saying it, or they are equivalent, they are making it equivalent as epsilon dash r omega equals to epsilon r omega plus I sigma r omega by omega. As we can see here, if we take minus of I omega common from here, so it will be remained as epsilon r omega, which is here. And if we take minus I omega from here, so it will be plus I upon omega sigma r omega. So they have taken this whole term as epsilon dash r omega. So this is the relation they were talking, uh, that the relation between conductivity and permittivity. So this is that relation. Here epsilon dash can be taken as the real part of epsilon. Now for graphene we have only given a two-dimensional conductivity and have to divide the thickness to obtain a three-dimensional conductivity. We find permittivity of graphene as this. So they have given here the final formula of permittivity of graphene: epsilon dash omega equals epsilon 0 into epsilon m omega. Now this term, as we have calculated, is the epsilon m omega term, and here epsilon r comma omega, they are taking it as epsilon 0, or one can say they are considering it as 1. Actually the epsilon r omega is being divided or written as epsilon 0, and if we take it common from here, so we get this expression epsilon omega equals to epsilon 0 1 plus I sigma 2d divided by epsilon 0 omega d. So this is the relation or the expression of the permittivity of graphene. Now the vanishing thickness limit, a Taylor expansion of the tangents hyperbolics for small arguments is given by tan h equals x minus x cube by 3 plus o x raised to the power of 5. So this is the expansion of tan hx. This is how they are expanding the dispersion relation earlier we discussed in terms of tan h or tan hyperbolic. And after solving it, they are saying in the last step we have included the relation permittivity of graphene here. So here in this step they are converting epsilon m into the permittivity of graphene. As we can see here, epsilon m is being converted to this whole thing, and they are putting the values here and finally giving the value of wave vector square kp square for the surface plasma polaton waves is as the value like this. So this is the value of the wave vector for surface plasma, sorry, polariton. Now where we have used the free space wave vector k naught equals omega by c. This is the free space wave vector, while kp is the surface plasma polariton wave vector. Here eta is the impedance taken as under root of mu by epsilon or mu naught by under root of epsilon 0 epsilon d of the surrounding medium in the last two steps. Here epsilon d is the permittivity uh, of the material just below graphene, and epsilon 0 is the permittivity of air just above the graphene. So these two values are there. They are giving the reference also. Uh, Hansen's dyadic Green's function and guided surface waves for a surface conductive model of graphene. This is the paper they have taken reference from for a derivation of this relation using other methods. The found dispersion relation, they are talking about this relation. The found dispersion relation allows some physical interpretation. We can see that if for a given frequency the conductivity approaches high values, Kp approximately equals epsilon d k naught square. Hence, graphene acts as a perfect metal as expected. They are saying that the surface plasmon polariton waves vector or wave vector for SPP approaches to epsilon d into k naught square, and this is the justification they are giving that graphene acts as a perfect metal. On the other hand, if we look at the conductivity again and set scattering rate, here gamma is scattering rate or the rate of relaxation. So if they are taking it as 0, then sigma 2d is purely imaginary function. Means the conductivity of graphene becomes purely imaginary. So for low conductivities, they are saying that for low conductivities of graphene, Kp is very greater than K naught, and this makes it possible to build resonant graphene devices. Here they are giving the justification that the Kp, which is comparatively very greater than K naught, makes the wavelength or lambda SPP of lambda of SPP waves very smaller than the wavelength of normal electromagnetic wave in free space. So since the wavelength as they are saying, this makes it possible to build resonant graphene devices that are much smaller than the wavelength. Since here they are talking about the wavelength of free space. Suppose if we target 1 terahertz electromagnetic wave or radio antenna, so for 1 terahertz the wavelength should be around 300 micrometer. But the surface plasmon polariton waves wavelength or lambda SPP will be very much smaller than lambda naught. So that's the reason that very small graphene devices or suppose antennas can be designed for very large wavelengths. Antennas in terahertz frequencies, for example, can be in the order of just a few hundred of nanometers. So they are saying that just few hundred of nanometers of wavelengths of several tens of microns. Suppose the wavelength of the antenna is 100 microns, and the size of the patch or the antenna is of 1 micron. So here normally the principle says that the size of the antenna should be half of its wavelength at least. Then only the electromagnetic wave will propagate through it. But because of surface plasmon polaritons, the wavelength, the SPP wavelength becomes very smaller than the normal or free space wavelength of that frequency. That's the reason it is possible to design very small devices for the same wavelength, for which other material means other than graphene material would be giving a very large antenna. So uh, this is the plus point of graphene. Now they have given some background of graphene also. Background: graphene, a material with tunable conductivity. Here they have talked about its tunability. The main results for the physical quantities of graphene follow from calculations which are a little too complex to be presented here. So they are showing the complexity of graphene's conductivity. That's why they are giving it in short. In short, the properties of the material are related to its conductivity sigma 2d. Furthermore, sigma 2d can be tuned using the electric field effect, applying a certain voltage difference to a surrounding material. Suppose graphene is placed on the silicon dioxide material, and the thickness of the silicon dioxide material is also not very large. It should be around 1 to 2 micrometer. So if electric field effect is applied in terms of certain voltage difference, between that material, I mean between graphene and that material, then the conductivity of graphene can be tuned. These two properties can be seen as the reason why enormous effort is put into the research relating to graphene at the moment. So they are giving it important that the tunability of graphene is an important effect, which is uh, which is making graphene more famous. The EFE or electric field effect changes the so-called chemical potential. So because of the electric field effect, chemical potential is changed, and chemical potential is a term, an important term in the formula of graphene's conductivity, as we can see it here. Sigma 2d equals this. Here mu c is the chemical potential they are talking about, which is dependent upon the electric field effect. So by changing the electric field or applying certain voltage, we can change chemical potential, and this is how we can change the conductivity of graphene. Here T is the temperature, gamma is a rate corresponding to relaxation process. One can call it a scattering rate. We are furthermore in the frequency domain with an exponential minus of I omega t time dependence. So they are explaining about the time dependence in terms of e raised power minus of I omega t. In the literature, you can find mu c approximately equals 50 to 1000 milli electron volts. So they are giving the characteristic value of chemical potential that it should be around 50 to 1000 milli electron volt, and the scattering rate value should be less than or equals to 1 milli electron volt. Now we want to model this two-dimensional conductivity to be able to do electrodynamic calculations or on a computer. A very decent way to do so is to find a representation of graphene as a thin three-dimensional layer with a certain permittivity supporting collective electron oscillation called surface plasmon polaritons. Here, this is the short definition of surface plasmon polaritons. It is collective electron oscillation on the surface of graphene layer with a certain permittivity supporting collective electron oscillation called surface plasmon polaritons. See right figure here, they have shown this thing. As we can see, the arrow is showing the propagation of surface plasmon polaritons. With this trick, sophisticated computations are possible and application of graphene can be designed. Here they have given some links also: graphene plasmonics antenna for terahertz spectroscopy. In that link they have shown about or they have explained graphene plasmonic. So I recommend you people to guys please visit this website, photonics101.com, as they have given enormous and very concise information about graphene and its behavior, its chemistry, its physics. They have explained it very well and up to the point. They have given some warning also. After this analysis, note that the permittivity we have derived is just the dispersion relation of a kind of supported modes. They are seeing that the permittivity value they have derived the formula. It is just a form of the dispersion relation of graphene for supported modes and transverse magnetic SPPs, not of anything that can happen. So they say that it's just a hypothesis or a or a experiment, one can say. They are not saying that or giving a statement that it is valid for all and for every applications. So they are saying it to use it carefully. Well, they have explained it quite well, and I think one can go further for graphene knowledge and information using the facts they have given of graphene here. So thank you guys. That's it for now. Please visit the website photonics101.com for further information regarding graphene and its behavior. Thank you.